Okay, bonjour. So today is another Darko and Bruno talks about biostat and AI. And today, Darko is my favorite type of topic because we talk about a historical figure or historical concept. And today we're going to talk about this gentleman here, right? Who was born in what, 17, in the 17, what was it again? 17?
17, somewhere 77 or
The
something like
late
that.
1700.
Yeah,
And
yeah.
is German. His name is Carl Gauss. We're going to talk about the normal distribution, and maybe as we sometimes do at the end, Darko and I go post Gaussian. We invent a new. So that's why you have to stick until the end, because at the end we'll announce our post Gaussian, neo Gaussian, maybe anti Gaussian paradigm, and that might have a huge impact on both AI, biostatistical concept, and the world as we know it. So, who was? I'm asking you the question, Darko. Who was Carl Gustav Friedrich? I'm probably mixing up his middle name, Gauss. And I still don't know if it's Gauss or Gauss or Gauss.
It's actually, there are so many ways you can pronounce it. But Carl Friedrich Gauss, actually a German mathematician from 18th century, as you said, and is very famous in statistics because he actually popularized. Many would say that he invented, but he actually kind of structured and popularized this bell-shaped distribution that we use very frequently in statistics, and we call it the Gaussian distribution. And you
Now, I've
can
got a
see,
question. You
okay,
say, was he popular with the ladies?
oh, I think his distribution of popularity was quite good, if I may answer that way.
He looks like he was popular with the ladies. Shahir Sheikh, um, uh, producer extraordinaire, in parallel will check on ChatGPT and tell us about Gustav Gauss, sort of love life and family life
This
with his
is
funny
Shahir
hat.
Sheikh checking in from the background. I have a question for you, Mr. Bruno Larvo.
Yes.
How would ChatGPT know from 1777, somebody that was born in 1777?
Well,
How would ChatGPT tell you
well,
about
first,
your
well,
he
first,
was
look at him. Look at him. You can see right away that this man was popular with the ladies with his funny hat. No doubt. You can see he had a lot of game. You can see. You can. So, second, ChatGPT has read everything. There have been biographies on him. I'm sure it says something about his love life. So, let's ask. Let's figure out where he fits on the uh, normal distribution curve. Now, by the way, I've got a question for you, Darko. Is and again, I'm the naive guy in this dynamic duo. The normal distribution, the bell-shaped curve. Okay, is that when we have the in French we call it the écart-table, the medium, the whatever it's called, the thing on the side, the the distance, the average.
Yes,
Help me out.
yes, yeah. So we have, just as you said, we have the average in the middle, and then on the sides, as we go from the average, the curve is lower and lower, and we actually have a specific standard deviation that
Standard
defines
deviation. That's what I
standard
was making.
deviation. Yes.
So, did he
So,
invent a standard deviation?
well, he actually, we could say that he invented the way we look at the standard deviation in terms of this bell-shaped curve,
Because
right?
he
So
did
he
not
kind,
invent the bell shape. Everybody knew the bell before. I can guarantee that people knew the bell shape before him.
yeah, I think you're right. The bell appeared before him, even though
Right.
in the popular general wisdom we say, hey, he invented the bell-shaped curve, but it appered in so many
So
places
he
before.
discovered how to calculate standard deviation. That was his thing, I guess, right?
Yeah, so
He-
he discovered how to actually formalize all the formulas needed to calculate this distribution, and he actually related it to something that is very also very interesting, which is the central limit theorem. So why is this curve so special? Because there is this theorem that tells that no matter what other distribution you take, you don't have to take the bell shape. You can take some other, which is not bell shape. But eventually, if you take a lot of these distributions, random variables, a lot of these distributions, and you start doing some math around them, they will always converge to this bell-shaped distribution. So it was special. They started seeing it everywhere. Even if other distributions are not bell-shaped, eventually, if you repeat the experiment many, many times, most of the time they actually converge to this bell shape. And that's why he's famous. The Gauss, which I also agree, he definitely had a very good style, in that image. But what was so interesting about Gauss is that he called it the normal distribution, right? It's normal. Why is it normal? Well, because it kind of aligns with the central limit theorem, and all other distributions will kind of converge to this normal distribution if we observe them
Now,
many, many times.
I understood half of what you said.
Oh, that's good.
I'm sure the audience understood either the other half or all of it. By the way, if the audience has a question or a comment or love Carl Gauss or hate him, please comment, tell us, or ask us a question. Or if you did not understand everything, I did not understand everything, now is the right time. But here's my question to you. Is it like the frequentist or the Bayesian that you have pro and against Gaussian? Or no, now everybody's Gaussian. Everybody's Gaussian.
Yeah, almost. I mean, there is like a duality in statistics where we actually say, a lot of people focus too much on this normal Gaussian distribution because there are other distributions too. There are other distributions that live as well. But because it's very closely bound to this central limit theorem, there aren't really many statisticians that will say something against this distribution, right? The distribution on its own, it's quite concrete with proof and evidence. So there isn't really like a duality, frequentists versus Bayesians. And most people would accept the fact, most statisticians would accept the fact that Gaussian distribution is important in statistics.
So here's what I'd like to do. First, I'd like Shahir to tell us something interesting about the life, not the work, but the life of Mr. Gauss. And then I'd like you to try to explain to me what is a standard deviation. And assume that you have a 50% chance of succeeding explaining that to me.
As a Bayesian. As a Bayesian.
It's better. That's right. With your prior. Yeah. Was he a frequentist or a Bayesian, by the way?
Yeah, that's difficult to say because I think
he looks like a frequentist to me. I tell you the truth.
His look reminds me of Fisher. I don't know about you, but I mean, yes. Fisher had like this different style. He didn't wear hats and everything.
It's the same guy. Look, it's like Edith Fisher. we get to break through here, people. Fisher and Gauss is the same guy. You just put a hat on, shave it a little bit.
Yes,
it's the same guy.
Little bit, yeah, a little bit of styling and.
Right, Shahir, tell us something about Mr. Gauss before we go to the hard part of the conversation, which is trying to get me to understand what the standard deviation is.
So I've checked on ChatGPT. This is Shahir again, jumping in. And it suggests that he was not really admired, or should I say, there's no historical record, as you can see on the screen as well, suggesting that he was a social charmer or widely admired romantically, in case that helps, Bruno.
Okay, so I was wrong in my assumption. He didn't have a lot of ladies.
Well,
maybe he was...
The short answer, the short answer to the question if he was popular among ladies was not particularly by GPT itself. I'm checking the other LLM models in case they want to fight.
Because usually ChatGPT is trying to say something nice. So for it, not particularly, it might be terrible. Like it was like a recluse and didn't smell good. All right. Well, we'll have to figure out anything else interesting about Carl.
Well,
He looks interesting. I'll keep exploring and I'll keep
But,
jumping
right,
in. Over
right,
to you too,
right.
Darko and Bruno.
Back to okay, and so let's go to the curve, and most of the audience already knows exactly what a standard deviation is. So go slowly on me. All right. So I understand the mean. Okay, it's a middle. It's actually not the average, right? It's a mean. It's a median line that I understand. And then there's a two lines on both sides. What are they?
yes. So those two lines, even though not perfectly centered here as the way I sent them to Shahir, those two lines are actually the standard deviation. So the standard deviation, well, we can observe it as like a measure of how much our data varies, how much is the variability, the dispersion of our data relative to the mean. So you can see those two lines. It's actually mean plus or mean minus standard deviation. And again, the image may not be perfectly
I think
aligned,
that's the
but
wrong image. Shahir, can you find a better image? Because it's not standard. It's not the same on both sides. So
yeah.
maybe there's a better image.
So I sent this image to Shahir. So
Okay.
Shahir will probably find a better one. Yeah. Anyway, sorry, please go ahead.
No. So with that, so maybe using just words, the standard deviation is what?
Yeah. So we can. I think actually the term itself kind of tells a lot about the spirit. How much our data deviates left and right from this. If we observe that mean as the central line, the center, how much our data is dispersed, how much it deviates left and right from the mean. And standard deviation is a measure of that. So the larger the standard deviation, the larger the dispersion of the data left and right.
So the
of the
flatter
mean.
the hat or the flatter the bell. So there could be a very pointy hat,
Yes.
right? You will have a short standard deviation, right?
Yes.
But if the hat is or the bell is very, very flat and spread very, very, very long with a long tail on both sides, there'll be a very long standard deviation. Is that right?
Exactly. Exactly. So standard deviation kind of defines the shape of the how there are actually two parameters to define the bell curve, right? And thank you, Shahir, for a much better curve. Now, those two parameters are exactly as you said, mean and standard deviation. So mean is usually some number. It could be 0. Here it's 1,150. And then when we add standard deviation, we are actually defining the shape of the curve in terms of being more flat, more widespread distributed, or being more focused or more pointy, as you said. Now, why is this so important? Because in statistics, most of the time, the fact that we have smaller standard deviation in some result actually brings more confidence to us, because we say, well, this data is not varying too much, right? It's more pointy. It's more it's more focused around the specific line, around the specific parameter. Then we say we have more confidence in this result because it's not going to vary too much, right? So I know this may be a very simplistic explanation, but a very good point why standard deviation is very important. By the way, we can use standard deviation to calculate the confidence interval, right? So all those confidence intervals that we calculate in oncology, hazard ratios and everything, most of the time we calculate them by using standard deviation and then calculating from the standard deviation the confidence interval.
So, Darko, I understand 20%. Yes. We need to go very, very slow here for me. Right. So I understand it's a bell curve. Both sides are the same shape. There's a unit, whatever that is, 700, 850, 1000. There's a unit. By the way, is it normal that the curve touch? No, the curve doesn't touch at 0. It touches at 700. I understand that too. All right. I understand the mean, 1150. All right. Now, I think I understand the percentages, which is what percentage of the volume is within the lines. Yes? Did I get that
Yes.
right? All right. So,
Yes.
okay. So I'm now at 35% understanding, right? So, okay. Now, next, all right. So next, in each of the, and there's 6 segment, and I understand the percentage in them, right? It's a percentage of the volume, of the total volume under the curve. So I understand everything here, except there's no standard deviation here.
Actually, this may actually increase the percentage, which is that if you look at the bottom of the curve,
Yes.
yes, there is mean in the center, m, and then there is, if you go to the left and to the right, there is m plus 1 SD,
Yes.
mean plus 1 standard deviation, or mean minus 1 standard deviation. And then
Yes.
if we go even more, mean plus 2 standard deviations or mean minus 2 standard deviations, we actually see which percent of the curve we
Let me
cover.
interrupt you. I think I got it. All right, let me try that. Okay, the standard. Oh no! And then we got Gauss looking at me. He say, "Congratulations,
The
Bruno."
handsome Gauss, the handsome Gauss.
He said, "Congratulations, bro, you got it." Well, let's see. Let's see if I get it. All right.
He's reminding us
He's
to be
reminding-
careful.
He's judging me right now. He's judging me. All right. Oh no! All right,
Oh,
yeah,
we'll be
all right,
okay. We'll be good. We'll
yeah,
behave.
all right. Okay. Let me try it, Mr. Gauss. The standard deviation. The standard deviation. Don't tell me another way. Is it? Stop it! I need the standard deviation is the number left and right of the mean. Okay, the number left and right of the mean, and it just right. So that between these two numbers, you've got 68% of the volume under the curve. If you draw a line, you've got 68% of all the volume between the -1 and the +1 standard deviation. Now, why 68? I don't know. There's a reason, I guess. But yeah, it says 68 at the top. That's right. So between the -1 and +1 standard deviation represent 68% of the volume under the curve. But why 68? So I understood what it is. I think I got it, right? That's
Yes,
it.
you got it.
I
it.
know. So 68% is, or 34. Maybe it's because it's, so why 68? Why is it, sounds arbitrary as a number?
Well, I think that's maybe that aligns with the core of our topic today, which is the Gaussian distribution. So the way this distribution is defined by formulas, and according to this central limit theorem as well, it kind of follows a specific shape. And that shape, when we look at the area under this curve, right? So area under this curve, given this shape that again is defined by specific mathematical formulas and proofs, will define that this is exactly that percent. Now, I think you're very close to understanding the statistically significant percent, which is 95, right? 95%, like the p-value. And look now what happens. You just mentioned 68%, right? 1 standard deviation. But look, if we start to go 2 standard deviations, like m plus 2,
95%.
95%.
Oh, 0.05 p-value.
The p-value.
Bingo.
Bingo. And basically, a lot of p-values in statistics are calculated exactly this way. So we take a portion of the curve and we say, this is 95%. This is
okay. I get it. I mean, I don't know if I got everything, but I got a lot more. So the p-value in Biostat is based on 2 standard deviations. Right?
Basically, I mean, there are situations where the p-value, there are other ways to calculate the p-value, right? This is just one of them, which is very popular and is used very abundantly, right? But there are other ways. We have to say that.
I understand, and we don't want to get into the Bayesian discussion again. That, so by nature, that means that Gaussians are frequentist because they deal with p-value and right. So actually, they are frequentist.
Yes, and basically, even this bell-shaped curve, we could take some other distribution. It doesn't have to be bell-shaped. But if you keep repeating the experiment and calculating the means in those experiments, and then just try to plot those means on a curve like this, they would converge to the exact bell shape that we have here. And that is very interesting. It happens in statistics, and we can only explain mathematically why it happens.
Okay, so is it an experimental or is it a theoretical effort? In other words, he just said, well, in nature, you know what? We found a lot of curves that are like this, and curve in which if you split if you split the whole thing, you end up with that shape, that and then it's sort of, because you could imagine a hat, a bell, in which much flatter. It has the same top, and then if long tail on both sides. Would it be Gaussian or not anymore? No.
In theory, it could be if it follows the same shape. Like it could be a very narrow bell, but it's still a bell. But as you said, it could also, if it breaks the shape, if it's like going straight and then to the right, it's no longer a Gaussian, right? It's now the only definition that's important there is the shape. Now the shape can be flat, it can be very narrow, and still remain Gaussian.
But in order for a curve to be Gaussian, okay, in order for a curve to be Gaussian, it cannot continue too long on both sides, right? It needs to hit zero pretty much at 2 standard deviation on both sides. If it doesn't hit zero or nearly zero, it's not Gaussian anymore. It's something else.
Yeah, so it cannot go indefinitely, right? It can get close to indefinitely, but as you said, it cannot go indefinitely in the sides. And
right.
Yes, then it would.
Yeah, 99.7% needs to be
3 standard deviations.
Right. Yeah. So I think I got 68% of it.
Well,
68.
You were at one.
Left,
One standard. You understood one standard deviation from the mean.
So if something is 1 standard deviation from the mean, it means that you're pretty close to the mean, I guess.
Yes.
Okay, and then there's math to deal with all of that and do interesting things. This Carl Gauss was a smart fellow. I like it. Yes. And each time we use a p-value in Biostat, we have to thank. Maybe he wasn't a ladies' man after all, but he did something good for us.
Yes, it was a smart man, and he changed science definitely. With his interesting. He had a very interesting hat.
I don't know if he had a big impact on fashion. That we're not sure.
I think his style is so good that he could actually show up. His style could be even popular today.
I think so. I think in San Francisco, I see a guy dressed exactly like that yesterday.
Yeah.
Maybe it was him.
Let's call it the Gaussian style.
The Gaussian style.
Yeah.
No. A bit of a black hat and a big collar, open collar. That's it.
Yeah.
And a mysterious smile. I think we got it. I think that's going to be our closing line. So we should all be thankful for Carl Friedrich Gauss and reflect this weekend on how normal distribution can help us in our day-to-day life as well as in our professions.
I agree. We use it a lot in science, research, statistics. There are other distributions which are equally important, right? Let's not call them the paranormal, they're also normal in a way. There are no ghosts or nothing paranormal, but I agree. The Gaussian distribution and this mathematician, we should all be thankful for his contributions.
We should have a future podcast in one of our historical podcasts. Should say post-Gaussian, right? So non-Gaussian curves, and we look at all the non-Gaussian curves. We do a quick recap to make sure I didn't forget what Gaussian meant. You can test me, and then we can have non-normal distributions. And
Yeah.
what does it mean in our day-to-day life, right?
Yes.
So-
we go full paranormal.
Paranormal. Yeah, that's right. We're paranormal. Abnormal, paranormal. Good. Well, Darko, thank you for helping me go from 35% understanding or 34% understanding to 64%.
No, 68.
68%
68.
understanding. And I'm sure that Shahir, I think, is probably at 95%. So as a team, we're moving down the curve here. Thank you.
Thank you so much. It was really a pleasure to chat with you and Shahir. And au revoir.
Au revoir.